Good afternoon, everyone. So it's my pleasure to present you some part of what we did in Grenoble. So maybe I will just switch off my camera to have all the bandwidth for the presentation. And so let's start with the presentation itself. It will deal about Raspberry cluster for how to validate distributed control in microgrid. I'm very happy to present that based on the different works that have been done by GAVRILUTA, that was a postdoc in Grenoble, that is now in AIT in Austria, and as well by a colleague that was PhD student in Grenoble, Tung Lam Nguyen, that is now back in Vietnam. And so it's this has been done in the Grenoble INP. So Grenoble INP is Institute of Engineering and Management of University Grenoble Alpes. And in fact, G2E Lab is electrical engineering laboratory of Grenoble, having some resources both in Grenoble INP as Institute of Engineering, but as well some professors, associate professors coming from Université Grenoble Alpes itself. And as well, we have researcher coming from CNRS. G2E Lab is hosting, in fact, many teams working in electrical engineering. And I'm working in, this is the largest academic team in power system in Europe. We are having, we are hosting more than 36 PhD students, and the name of the team is Cyril team. I'm co-head of this team. And presentation of today is related to a work that did start a few years ago about how to try to validate distributed control. And in fact, everything started with a specific project funded by ANR, which is type of National Science Foundation you can find in US. And it's the name of the project is Sogreen Project. And it was about how to put more distribution of intelligence and control in the smart grid to support wireless cellular network. And so, I mean, from a centralized viewpoint, you have the typical classical vertically integrated power systems. And the idea was to say, okay, in the future, what will happen? And especially with a more distributed viewpoint, how will interact both power systems, including flexibilities and let's say smart grids in general, with the communication infrastructure that are, of course, everyone knows they are more and more interconnected. So anyway, it was really about optimal control of small based station. So the aim was really to create some base units for the communication supplied by both the grid and some distributed control and distributed energy production from PV and a local storage. Why it's a big deal and hot topic in France and in many countries in the world, just because mobile traffic is exploding. We're having more and more data flowing and more consumption for this specific infrastructure. So going from 4G to 5G may solve some issues about let's say consumption, but still if the data flow is still growing up, we will still face some issues about consumption. But anyway, operator costs on the side of telecommunication companies are still increasing, and you need, of course, to work as quickly as possible on how to reduce CO2 footprint. And that's why those small base station for communication on, let's say, some range of 10 to 100 meters need to be self-supplied, or at least having some local generation with local storage as well to increase the resiliency of the system. So the aim of the project was really how to joint optimize wireless cellular network and associated power grid, and really the creation of a cyber-physical framework for real-time distributed control and optimization in smart grids. That was really our aim in this project. We were working with colleagues from CEA and from University in Paris, Telecom Paris Tech, and we were really interested in this complex interconnection between communication and power flow. What was our proposition? And let's focus on practical objective about what we did develop. We wanted to be able to develop a distributed control, and so that's why we started to propose a platform for testing distributed application in the electrical grid, which was built around Opal RT that we are extensively using in power engineering. And the idea was to create a platform that was low cost and developed using open source resources, so to test interactions between ICT and power systems. We had as well many other theoretical objectives on the line, but that's more or less all the practical objectives we had in mind. So again, Opal RT is simulating the real-time system, and host measurements web server, that is a slight modification of Opal RT, and then communication with Ethernet router, so to give the data to some distributed devices. That was a fleet of Raspberry, and those Raspberry are either able to communicate through, again, the Ethernet router, or communicate through a wireless infrastructure with a Wi-Fi infrastructure, so to have the connection between them going as well through a XMPP server. So that's more or less the architecture we did develop. And so to give an overview, there is a physical system that is fully simulated into Opal RT, and then hosting by the server of Opal, we did add a asynchronous communication block. So being able to communicate the different data of interest, frequency, voltage, and so on. So through a UDP communication web server, we're able to go to the data server, XMPP, and thanks to a communication, able to send information to the various agents that are discussing together, coordinating themselves, and sending back their, let's say, control, local control, to the various implementation of physical-based simulation inside Opal. So showing it another way, again, Opal RT server communicating through Ethernet switch with the different Raspberry, and Raspberry are able to get, of course, information at low level, but they are able as well to discuss with each other, exchanging data and being able to implement what we did test. And what we did test was about alternative direction of multiplier, for instance. So being able to control. So I will present two use cases in a few minutes, one about DC microgrid and one other one about AC microgrid. So the implementation is the following. Maybe I can zoom in a little bit. So we have the fleet of Raspberry. Here you have 10 of them connected to a Cisco switch. And the we cannot see here the Opal RT because he's behind here. And this is a control desktop allowing us to set up the different communication and having access to the various Raspberry, so to make some configuration. And so zooming a little bit, as you can see, the various Raspberry Pi are, of course, hardwired communicating through Ethernet, but they can communicate as well. As you can see here, there is a Wi-Fi switch. They can have so different way of communication. So if you really want to separate, to split the communication, being sure that there is no interferences. First use case I want to present, and it was part of the work of Catalin in Grenoble. It was about distributed control of a DC microgrid, and so you will be able to get the various information or to download the existing paper on the subject. And so the idea was to test ADMM algorithm with a 12 millisecond inter-agent communication delay. So this is achieved thanks to the Ethernet hardwire communication, and with a limited amount of iteration, we were able to show that even with a distributed control, after a few iterations, we are getting exactly the same solution as you would get from a centralized implementation of the optimal power flow system. And even if there are some slight uncertainty and difference on the different communication, and as well on the various computation that you can get inside the different Raspberry, we were able to get the let's say optimization done very quickly at a third level control. A second test case was about AC microgrid, a more smaller one, as you can see here with the line impedance. And so the idea was to have agents playing not at the primary control loop. This was implemented in Opal RT, but giving information about what is the best voltage value, frequency restoration, and power sharing and state of charge balancing. And this was computed with a distributed approach with this the same spirit of alternative direction of multiplier, so to get the the optimal control. So we can see here the convergence of the computation algorithm thanks to the coordination between the different agents embedded in the Raspberry Pi. A second test case that was done with the same implementation, but with a real energy storage system and a power interface. So with power hardware on the loop. That's what we did create together with colleagues from UK. And so there is the detail in the paper that is presented below, and as well in the thesis that is completely public. You can access through the internet. What was interesting here was the test of a plug and play feature, so you can disconnect, connect, control of a power hardware, energy storage system, namely. That was really interesting in this spirit of getting, the agent-based world supporting the smart grid and the microgrid with this ability to connect new devices and make them self-coordinating for the sake of the microgrid. We were as well testing optimal power flow control. So first one was really centered on secondary control. We did test as well tertiary control, again to have convergency of the ADMM process toward the same value we would get thanks to a centralized approach. With, of course, we were doing some disturbances. So red line is what would be the best guess from a centralized viewpoint, and the green is the convergence and the value we are getting after a given amount of iterations. So thanks a lot for your attention. I will stop here, and if you have any question, I will be very happy to discuss with you later.